This is our speaker today needs no introduction. There's no introduction, whatever you prefer. Pravesh will be at Princeton next year and is here this semester. Tell us about this major breakthrough.
Well, thank you, Zev. The right description of this talk is that it is basically Zev with cover band playing. Last year, Zev gave like a long 2-hour lecture, I think also on a Tuesday, about locally correctable codes, locally decodable codes, what we know about them, etc. Like he went into like lots of details about constructions and lower bounds and stuff. And basically, you get to see the cheap second act. That's what I'm going to do today. Okay. So the talk is actually very useful. I highly recommend watching Zev's talk if you get at all interested in this topic. It's a great primer. I'll try to tell you only like briefly because I want to tell you, okay, how the proof works. And anyway, all right. So yeah, this is joint work with Peter Manohar from CMU. He's a 5th-year graduating PhD student. This work wouldn't have happened without him. He's amazing, and the great thing is that he'll be at the IIS in about 6 months. So you can ask him all the gory details of the proof. He will tell you way better than me how they work. Okay, excellent. Now, I've got a cheat sheet which I'll use to save 10 minutes, which is basically things I want to remind you about basic coding theory. Okay, I'm sure most of you have seen it before. Otherwise, I'm just going to take like 5 minutes to describe it, which is also nice because if you're late, like 5 to 10 minutes, you will not miss anything. Good. All right. So we're going to look at error correcting codes. For me today, they are simply maps that take k bits and send them into n bits and larger than k. It's like in some sense introducing redundancy on the top of your k bits with the idea that if you think of k bit as your message, like things you want to actually send to someone, what you transmit instead is the code word, like this padded version, this redundancy added version. And the idea is that because of this redundancy, even if there are corruptions or modifications to the transmitted message, you can still correctly, reliably, uniquely recover the message I intended to send. Okay, that's the very basic idea of coding theory. And the basic central parameter that governs what fraction of errors you can actually correct is the distance of the code, which is defined over here. So, it is simply the minimum over all possible pairs of distinct messages. In this talk, B and B prime, these letters like B would always mean messages. So for any B not equal to B prime, it's the number of bits of the code word of B and B prime that they are different on, normalized by the total number of bits. So this is a fraction in 0, 1. Okay. So this distance simply counts what is the minimum fraction of bits that are different in the code word of any two messages. Okay. The messages could differ in only 1 bit, but usually the code words will differ in a lot more. Okay. And roughly speaking, the distance up to a factor of half governs the fraction of errors you can correct. The idea is very simple. In some sense, you can imagine some canonical decoding algorithm that simply takes, a corrupted code word and sends it to the nearest possible valid code word. And if like every 2 code words are distance far, then as long as your number of corruptions is less than half of the distance, you will get a unique correct answer. That's it. That's basically the idea. All of this is like more than 75 years old, in Shannon's original paper. In fact, Shannon already showed that there are great codes, and great codes in this talk refer to objects which stretch the message length by a constant factor while allowing you to correct constant fraction of errors. Okay. So the distance is some constant like 1% and n is order of k, and such codes exist. In fact, Shannon proved that random codes are good. So, it's not only they exist, they're abundant in some sense. Great. In fact, in this talk, I'm only going to look at a special class of codes, which are linear codes. What does linear mean? So I'm going to think of 0, 1 to the k as basically f2 to the k. So the vector space, f2 to the k. And I'm going to look at the domain, the output domain as f2 to the n. And then a linear code is simply a code where the encoding map E is a linear function. Okay. All good? Makes sense so far? Okay, very good. Excellent. So, even though this seems like a restriction, by the way, like 99.99% of the codes that we have are basically linear. Almost everything we do is with linear codes. In fact, Shannon already proved that random linear codes are good. So also, his result. Great. So that's basic coding theory. You know everything about it now. So I'm going to care about codes that allow a extremely simple correction algorithm today. Okay. So because I'm going to look for an extremely simple algorithm that allows fixing errors, this is like a significant restriction on the construction of the code itself. And the overarching question is, are there such codes? And if there are such codes, what is the minimum amount of redundancy they're going to need? This is like, the motivation, okay? So I'm going to look at codes that allow what is called as local correction algorithm, okay? What does that mean? Well, it's an algorithm to take some input, has some output. The input to a local correction algorithm is a corruption of a code word, okay? So a code word is simply, every point in the image of the map E. Imagine that I take one such point, X. X, by the way, would always be in the stock in the, 0, 1 to the n space, the code word space. Think of taking a delta corruption of X, which means that take any point Y, which in a normalized Hamming distance sense is at most delta away from X. In addition, the algorithm also takes input a coordinate index I. So, it tell me the nth, like ith bit, okay? And the goal of the algorithm is to basically take Y and I as input and correctly determine X sub I, the ith bit of the true uncorrupted original code word X, okay? So so far it's just a, correction algorithm. The locality means that the algorithm should work by reading Y in at most Q bits. Okay, so Q is the so-called query complexity of the algorithm. And the idea is that the algorithm should be able to read just Q bits. And Q, for the purpose of this talk, is actually going to be 3. So think of Q as very, very small, 2 or 3. So our goal is to somehow, decode the ith bit of the uncorrupted code word we intended to send by reading, let's say, 2 or 3 bits of, the corrupted code word. Okay? So this algorithm, you can see, has 2 relevant parameters that you see already, Q and delta. Delta is the fraction of corruptions it can tolerate, and Q is the number of queries it needs to decode any bit of the transmitted code word. Now, any such algorithm needs to be randomized, right? Because if it's not, say you say that I'm going to read only the first 3 bits, I have delta fraction of errors that I can create, and I can just choose them to be on the first 3 bits. So because this algorithm is going to be randomized, it's going to have some probability of failure, okay? And this probability of failure, of course, in general would depend on delta, okay? And I'm going to encode that by the 3rd parameter. So I just want the algorithm to succeed with, let's say, probability half plus epsilon. So I want it to have advantage over random guessing of epsilon, okay? Does it make sense? Local correction algorithm? Excellent. Just want to stress, for people who may not have seen this before, the only randomness here is the algorithm's random bits, okay? Nothing else is random. The input is, worst case corruption of a code word X. It's a worst case bit I, okay? The algorithm tosses random points, and, the only cause of failure is like, some bad randomness, okay? Good. And, relatedly, I'm interested in correcting every bit. Say you wanted to correct, I don't know, only 1 minus delta fraction of the bits. That's very, very easy. Just output the bit of Y itself. The hard part, or the interesting part, is that you need to correct every bit. You need to correctly report every bit of X. Okay. All right. Good. So you know everything about local correction algorithms now. So the obvious question is, are there codes that admit, local correction algorithms like this? You can see, this is what I promised. It's a very, very simple, very, very local correction procedure. I'm asking something a lot from the code itself. So the question is, are there such codes, right? So let's maybe right here. What do you think about Q equals 1? Could there be a 1 query locally correctable code? can think about it. This is, in some sense, very easy to see that it's clearly impossible. If you read only one bit, there's nothing you can do. So, that's good to know. What about Q equals 2? Are there 2 query local correctable codes? It turns out there is, and I'm going to tell you what it is so that you have some intuition about how these things actually look. Okay. Here's what my code is going to be. The encoding map. So I'm going to just think of, x as coefficients of a linear function on f2 to the k. So remember I had like, a message is like some bit vector b. I think of it as like some, element of f2 to the k. And the code is simply evaluation of all possible linear functions on f2 to the k. Okay. So you can think of it as E of b coordinate at any alpha equals b dot alpha, and this is all happening, mod 2. It's all happening over f sub 2. Okay. So what is n here? N is clearly 2 to the k, or okay, you could say like the constant part, so 2 to the k minus 1, right? So this is a code that blows up the message by an exponential amount. Okay. It's a linear code. It's obvious because, in some sense, it's linear in its first argument, the coefficients of the linear function. Moreover, it is also locally correctable with 2 queries. Okay. And let me briefly tell you why. I'm not going to do any proofs in this part of the talk. So how would I, imagine that I want to correct some bit. Okay. Imagine that I want to correct. So let's say I got y, which is a corruption of, this vector of evaluations of linear function, with coefficients b. And I want to, correct the bit indexed by some beta. So I want to correctly determine b dot beta. How would I do it? How would I do it? Well, if I just query beta, I don't know why sub beta could be corrupted. That would be bad. So instead, what am I going to do? Well, I'm going to choose a random alpha. Okay. And then query alpha and alpha plus beta. Okay. Now, what's the distribution of alpha? It's uniform. The distribution of alpha plus beta is also uniform. So, individually, they're correlated, of course, but individually, both alpha and alpha plus beta is distributed uniformly in the space of like the codeword bits. If a constant fraction of the bits are corrupted, like delta fraction, then with probability 1 minus 2 delta, both of these bits would be correct in Y. Moreover, if I just add those bits, then alpha cancels out, and I basically get the value of beta. And this is using the fact that, the encoding was, evaluation of a linear function. Okay. So I basically gave you a 2 query local correction procedure, right? And it works with probability 1 minus 2 times delta. Is it all clear? Okay. So I've given you a 2 LCC. That's great, right? Like start of the talk. Okay, I've spent 15 minutes, but you already know 1 locally correctable code. But it's, you could say it's exponential. It's blowing up the block length. The length of the code is like exponential in the message length. Is there a better code? Okay. It turns out basically that there is no better code. I'm going to come again to the issue of lower bounds in a bit, but right now I'll just tell you that even though this feels like a really expensive code, it's a price that you need to pay if you want a 2 query local correction algorithm. Okay, great. So onwards, you could ask, what about Q equals 3? Okay, now I give you one more query. What can you do with it? And the idea is in some sense quite natural. It is so natural that it's at least 60 plus years old. The idea is like these were evaluations of linear, like you thought of the message as coefficients of a linear function, and then the code was evaluation of this linear function on all possible points. Now we're going to think of the message as coefficients of a quadratic function, a polynomial of degree 2, and report the evaluation of this polynomial at all points. That's it. Okay. So imagine that, you think of k as roughly m square, where m is the number of variables of this polynomial. It's a degree 2 polynomial, so it should have roughly like square of the number of variables, possible monomials. Each of them gets a coefficient. So, my b becomes coefficients of this degree 2 polynomial. K becomes something like m squared. And I evaluate it at all possible 2 to the m points. Okay. So, you can see that in k, the number of evaluations is 2 to the square root of k. So I've saved a little bit on the exponential. 2 to the k went to 2 to the square root of k. Okay. I'm going to be still hand wavy here. But notice that you can actually locally correct this in 3 queries. Where does 3 come from? 3 is 1 more than the degree of the polynomial. The idea is that instead of querying, so if I want to learn the value of the evaluation of this polynomial at some point, which is basically the bit I'm interested in, what I'm going to do instead is query 3 points in a line. So, I'll take, let's say, I'm interested in beta. I'll pass some curve through beta, like a parameterized curve, right? A curve is parameterized by, some single parameter. Think of like projecting the polynomial to become univariate in that parameter, and then query on this curve 3 points, okay? You will again be able to show that these 3 points are uniformly distributed. So you will basically, with 1 minus 3 delta probability, get all 3 correctly from the corrupted code word. And now you can do polynomial interpolation on this curve. It's a univariate polynomial. It's a degree 2 polynomial. So if I give you 3 points, there is a unique polynomial that passes through them, and basically learn the value of beta. Learn the value at beta.
It's be a straight line for this to stay quadratic.
Oh, yes. Sorry. Well, a line is a curve. Yes. Yeah, sorry, my images are a little bit off. Okay. Does it make sense though? And you can push this idea to higher degree polynomials. The number of queries would always be 1 plus the degree of the polynomial. And the block length of the code basically drops in the exponent. So in general, you can get a 2 to the k to the 1 over q minus 1 length code with q queries. Okay. So now, one, piece of disclaimer before I move ahead. I'm restricting to all f2 to the k, etc. here. But all of this descriptions, all of what I'm telling you in a somewhat hand-wavy way, works on arbitrary finite fields. Okay, everything we are talking about is going to be like linear codes over arbitrary finite fields. So, you can think of the same evaluation of polynomials, etc., making sense over f sub p instead of just f sub q. Okay. I didn't want to use f sub q because q is the number of queries, and I'm going to avoid writing this notation down so that my letters are saved. Okay. But everything, makes sense on larger finite fields, etc. Okay. So what I've just described to you is, the Reed-Muller codes. Okay. And Reed-Muller codes basically give you Q LCCs with, exponential, but somewhat better in the exponent kind of codes. Okay. Good. So that's RM codes. And you can ask, as usual, are there better codes? Okay. For q equals 3, for example, you can ask, are there better codes? So we'll hold that question for a little bit, even though you know the answer in some sense. Introduce one more character to the story, okay, which is a slightly weaker condition than local correction. So for about, I was talking about this with Zev, who, is the source of almost all my knowledge on this topic. So it turns out till about 2007 or 8, people did not really distinguish between, distinguish very clearly between these ideas of local correction and the relaxation I'm going to introduce called local decoding. And in some sense, the punchline at the top is that these concepts are really different. Okay, so one consequence of this result would be that these things are very different. But I'm going to explain to you what this, slightly weaker condition is, and then come back to the question of are there better codes. It's very nice because Klim, is on the call, and this will allow me to reference a very, very cool result of Klim. Good. So I'm going to actually, I will not write down, but just maybe wave my hands here. Okay. So local correction meant that you can actually correct each and every bit of the code word by reading only q bits of the corrupted code word. Yes. Local decoding would be a relaxation where I only ask you to correct k out of the n bits. Okay. Remember, k is the length of the message. I don't want you to correct all n bits. I only want you to correct k of the n bits. Okay. Now, you might be wondering, why should I worry about this? What's so special about k? So towards this, I want to notice the following. This example, this code that we saw, by the way, I should have given the name. This first exponential size code we saw is called the Hadamard code. So the Hadamard code we saw is an example of a systematic code. A systematic code, is simply a code which has the following additional property, that the first k bits are in fact just the message repeated. Okay, so the code looks like, the first k bits are the message, and then, you have some, some functions of the message in order to allow redundancy. Okay. And it turns out basically that this is without the loss of generality. Every linear code is systematic without loss of generality. It turns out, in fact, every non-linear code also, in an appropriate sense, is systematic without the loss of generality, but I won't discuss that too much today. Okay. So what that means is that you can always assume that the first k bits of the code word are simply the message itself. And local decoding means that you can actually correct those k bits. In other words, you can decode any bit of the original message B by reading only constant number of bits, q bits, of the corrupted code word, but you can't quite say anything about the remaining n minus k bits. Did that make sense? Yeah, I'm trying to save like valuable real estate on the board, so I'm trying not to write too much. Okay. Good. So, this does feel like a relaxation. Nevertheless, in some sense, the construction that we knew of two query LCCs is also the best two query LDC. So, this code that I showed you that can correct every bit of the code word. If you only wanted to correct only the first k bits, it's not like you can do much better. It's basically also the right answer there for two queries. Okay. So let's come back to the question of, are there better three query words? Okay. And the first time, in some sense, this notion of local decoding versus local correction became really important is because in 2008, two researchers managed to construct a significantly better code than Hadamard, a truly subexponential length code, which allows local decoding, but at least, so far as we knew, does not allow local correction. Okay, so I'm going to write down this result here. So it's result due to Yakanen and then due to Efremenko. Claim is basically in the audience here. And together, I'm not going to go into the details of, exactly how it happened, but together, the point is that we know codes. See if I can remember 2 to the 2 to the 2 to the 2 to the O tilde of square root of log k. It's smaller than every, like the exponent of 2 is smaller than every polynomial in k. So it's a sub-exponential length code. And what they showed is that 3 query LDCs with n at most this exist. Okay, in fact, these are also linear codes. In fact, everything I'm going to talk about are linear codes. So this also is a linear code. And it's based on like a very cool idea of matching vector families. I'm not going to describe them for you, but I'm going to write it down so that you can search if you haven't seen them before. And using like, whatever, like this matching vector families, they were able to construct these codes and argue that you can at least correct the first k bits. So technically, we do not quite know whether you can actually extend for the same kind of codes, in fact, literally the same codes, we didn't quite know if you can actually correct also the rest of the bits, but we suspected not, because the idea that we had for locally decoding the first k bits didn't seem to quite work for the other bits. Okay, so one corollary of the result I'm going to prove today is that these codes in particular are also not locally correctable because they have too small a length. Yes, sir.
So this correctability, is epsilon close to one of them that goes to 0, or is it just above half? Like
could you say that again?
The epsilon, like the advantage you get.
Yes, it should be a fixed constant.
So, but in the code that you just described, does it like go to 0 with the distance, or is it just?
It's a good question. I think it does go to 0 if the fraction of errors is smaller. Yes.
There's a variant of this that you can do for subconstant error.
Oh, I
Very
see.
small error. You can do decoding within the queries like you do in Reed-Muller.
I see. So you're saying like if the
Work with Buchanan myself and Gopala.
I see. Okay. Yeah, like I said, most of the questions I'm gonna do it this way.
The way to view these codes as Reed-Muller codes, but not using all the monomials of low degree, just a subset of them.
Right.
And
Right, yes.
You can treat them as low degree polynomials also.
Right. Yeah. Actually, yeah, I did want to make that point. Again, don't want to explain too much, but in some sense, you can think of this as like refinement of Reed-Muller codes, where you somehow keep some carefully chosen monomials in the polynomial. So it's a sparse polynomial instead of like all possible polynomials. Okay, that's one way to view it. Of course, like the set of monomials you keep is very structured, and it comes from like this so-called matching vector families. Good. So coming back to our story, for 3 queries, we now know a significantly better code with like truly subexponential block length than Hadamard. So you can ask, are there similar things for local correction if I wanted locally correctable codes? And in some sense, this was the first time I suppose people at least suspected that maybe local decodability is or could be, strictly easier to achieve than local correction. We didn't quite know how to prove it. And so, in order to tell you this part of the story, I'm going to tell you a little bit about lower bounds. Because how do you prove that there are no codes with like smaller length? You have to like invent methods to prove lower bounds, right? So this enterprise began with a paper of Katz and Trevisan, and this is I think 2000. Now again, I'm not gonna tell you a lot of details because it's slow to write on the board. But there is a quick succession of works here. Maybe I'll write down that is Andy Wolf, and that is Woodwright, Pavlov, Shulman, and Trevisan. So this is all happening, I guess, till 2004. The last one is from 2004. What basically, this succession of works proved is that for any 3 LDC, locally, so LDC now means locally decodable codes. For any 3 LDC, N must be, okay, now it's like the drum roll. And the answer is square, which seems like very, very far off from this number over here, but that's the best we've got. Okay, that's the best we got till like last year. I'm gonna come to what we were able to do last year, but this is what we knew. In some sense, there is a gradation of results like this. For every q, there is like some lower bound we can prove, where the exponent is like some function of q, but it's all polynomial and it's only worse than quadratic. Okay, so the state of affairs is kind of weird. We cannot actually, at least till like 2020 whatever 2, we did not know how to prove more than a quadratic lower bound for 3 LDCs. The best construction is non-trivial, but subexponential. Where's the answer in between? We don't know. Okay. So then last year, and this is a result that I almost completely proved for you. Last year with Al-Rabia, Guruswamy, and Peter, we proved that 3 LDCs, n must be up to some polylog factors k cubed. So we were able to add a factor of k. It's only interesting because, it's the factor of k on k square. So k square goes to k cubed. It's a little bit better, still ways off from the upper bound, but that's the best we can do. Yes.
What about 2 LDCs?
2 LDCs are tight. Sorry, I mentioned it here, but yeah. So in some sense, the only section of the story which is essentially complete is the case of 2 queries. So we know that 2 LDCs and 2 LCCs both basically, there's nothing better than Hadamard. You can improve the constants with some tweaks, but in the exponent, but nothing much. Okay.
Let me just this. 2 LDCs with blocks, where every query, the code has blocks, and you read the 2 blocks. That's still open.
Oh, I see.
Queries.
Okay, sorry, yeah. I spoke too soon. There are variants of 2 LDCs which are still open. Okay. The stuff on the board, like the kind of objects we're going to care about, for that part, the story of 2 queries is more or less settled. Clint, you also had a comment?
The same comment that was in audience.
Okay, excellent. Excellent. Okay, good. Yeah, feel free to stop me. Yes.
So do these lower bounds actually work only for linear codes or for everything?
Good. Yeah. So this lower bound also works for nonlinear. But the result I'm going to prove today, like the result, over there, that works only for linear. And I'll come back to where we use linearity in the proof. Yeah. Any other questions? Actually, we can pause. No problems.
So one thing I didn't quite get, so for
Yeah.
the 2 query LDC, is this there's a matching lower bound for this number?
For 2 query LDCs or LCCs, the best code is Hadamard, and we can prove that basically it's essentially tight. So you have to blow up exponentially whether you want a 2 LDC or not, 2 LDC or 2 LCC. Yes.
What's thought to be the right answer for 3 LDCs?
Okay. This is controversial. Yeah, okay. I'm on camera, so I guess I'll give you my opinion. I feel like there are super polynomial lower bounds, but I'll allow Klim to interject and tell me I'm wrong.
I have no clue, what's the truth.
Yeah. I think the serious answer is that we don't know. I suspect that there could be super polynomial lower bounds, but yeah, we don't know how to prove anything here.
It's good to mention that a random code is not an LDC. So there's even non-explicitly, there's no non-explicit instructions.
Good. Yes. Yeah. I should have made this point. Very good. Yeah. I don't even have to look at my notes because I have that. So yeah, let me make this point. It's an important point with regards to this local code. So I told you that good codes exist and you can establish this very, very easily. I mean, you do worry a lot about algorithms and all later on, but to show that good codes exist, meaning you can correct constant fraction of errors with only constant factor below, it's very easy to prove by just taking a random code or random linear code. You could ask, is there a non-explicit construction? Right? We don't know any construction. In fact, there is a natural random model which will describe, when I tell you how the proof works, and that model, that one could call a random, potentially random construction of LDC or LCC, you can prove it doesn't work. It's extremely bad. It doesn't even give as good as Hadamard. Okay. So in some sense, we are in a regime where we cannot think of any reasonable random model that has these properties. So all the questions I'm asking are really combinatorial questions. Are there objects like this? I'm not asking whether they're explicit or not. It's not a question of explicit constructions. It's not algorithmic at all. Everything is about existence of certain combinatorial objects. Good. All right. So, all right. So we can prove a little bit of a better lower bound for 3 LDCs. What should we do for 3 LCCs? So there's a lot of work, and I'm going to write that much on the board. There's a lot of work. There's in fact work trying to characterize the limitations of the lower bound techniques. So Zev, has in particular a paper with Avi and Shubhangi, I think. Oh no, I think with Gopi.
Gopi and
yeah, there are multiple. Okay, there are multiple works that try to formalize what is going on in the proof techniques for lower bounds. And then they show that, these techniques actually work for slightly general objects and LDCs. And for them, the lower bounds are tight. So this is the way you like somehow examine, it's like an introspective work, like, why are we unable to prove better lower bounds? Because something like this is going on. And, on the flip side, there's also works on like related notions of trying to prove lower bounds by, somehow restricted to the class of families and stuff, which also I'm not going to go into, but we know some results in that direction. But lots and lots of stuff is known here. Summary is that, we know concretely how to only prove like a cubic lower bound for LDCs. That seems way far off from the construction. So that brings me to the result. So today, I want to show you some ideas for the result that proves that for every linear tree LCC over some field F, N needs to be at least 2 to the K over. Okay, and I'm being hand wavy with like polylogs, etc. here. Okay, so that's like saying that, so now, think of F as F2 for a bit in order to examine this expression. Then this is saying that, N needs to grow exponentially in K to the 1/8. Okay. So when we saw the example of Reed-Muller codes, we know that N is at most 2 to the K to the 1/2 here. So 2 to the square root K is the upper bound. And now, we can prove a 2 to the K to the 1/8 lower bound. It's not quite at Reed-Muller. Towards the end, I can tell you a little bit more about whether we can get to Reed-Muller. I think we have some ideas that can make this 8.5 now. And I think there is some chance that you can push these techniques all the way to 2 to the K to the 1/3. The last factor of K, I'm not quite sure if we could remove it with the ideas we have so far. Good, so that's the result. And again, I'll pause here to see if there are questions before moving on.
So is the style of lower bound here very different from the ideas before?
So the style is actually similar in some sense to this. The philosophy is similar, and I'll discuss the philosophy. In some sense, like that is the key idea, so to speak. It's definitely different from like, the work still like 2004. Yeah, this work, has like maybe it's a very simple but new connection, and that new connection yields, I guess, major dividends here, and some minor dividends over there. Yeah, I'll tell you all about that, but yes. But yeah, the high level idea in both that cubic lower bound and this exponential lower bound is somewhat similar.
I have a question. Does dependence on F is essential? Does your lower bounds becomes worse when, like, it seems that connections should be vice versa around?
Yeah, it's a great question. It's an issue with the technique we have at the moment. In some sense, at the heart of it is like, some kind of a reduction from large field to small fields. And that reduction loses like this quadratic thing that we have over there. It's not clear that's the best way to do it. I guess I don't know. Yeah. So right now, in some sense, this exponential thing only makes sense for small fields. Think of like F as a constant or at most like polydog or whatever in the code word length. You could in principle like design codes over huge fields, and they would be very interesting objects. Like again, one of the topics I'm not going to talk too much about, but you can ask Zev about. So this result says nothing about like LCCs over very large fields. Good. Any other questions? All right. Good. So what I'm going to tell you now is how the proof works. Oh, I just realized that I did not give you spiel for why you should care at all, but you seem to be caring, so I'll skip it. Good. All right. But there are lots of applications. Again, ask Zev, or like, go check out the lecture notes from Zev's class. The earliest things, they appeared in the construction of PCPs. That's why people got very interested in them. There are private information retrieval protocols. There are worst case to average case reductions. There are connections to, conjectures about combinatorial designs in combinatorics. For example, the stuff we are proving today has some consequences to so-called Hamada conjecture in combinatorial design theory. Lots and lots of connections to ideal combinatorics, incident geometry. I'll not talk about it, but if you get interested in any of these words, Google them. Good. All right. So we'll come to the interesting part. We'll actually do the math. So first, I want to tell you the philosophy of the proof. Then I'll completely describe, the cubic lower bound. And then I'll at least prove a result for LCCs. So I don't think I'll be able to complete the whole lower bound, but I'll be able to prove like an interesting special case, which would hopefully be illuminating. So let me give you the spiel. I guess the spiel part I can write here. So if you ever taught a class on undergrad complexity, where you introduce the SAT problem, then the instructors I took the class from always mentioned that SAT is like the most fundamental problems of all, although Rahul differs. It might say MCSB. And one reason you might think that SAT is the greatest problem of all, because you can somehow reduce all of the problems to it. This is how it's usually presented when you introduce NP and all for the first time. And one thing, for example, we absolutely not fail to mention is the fact that you can even reduce truth of mathematical conjectures to just, checking satisfiability of a SAT formula, right? And then, undergrads get very excited. And then, they quite like, okay, maybe this is like in some formal sense true, but it's not like an approach for proving a conjecture. You can't like make a SAT formula out of your conjecture and then like, try to decide if it is satisfiable, right? One reason for why this philosophy doesn't work in general is that, it's not easy to check satisfiability of SAT formulas. It's a hard problem, as we all know, right? So what's the philosophy? The philosophy is that I'm actually going to apply this philosophy. I'm actually going to reduce to, solving XOR instead of SAT, which is an equally hard problem, as we all know. But then, somehow come up with XOR formulas that I can solve with my hand, and thereby, prove lower bounds. Okay, so this is the basic spiel that we're going to make this undergrad class philosophy that we try to excite people with actually, live up to its name. Okay, so a little bit more in detail. What I'm going to do is take, the task of verifying that some combinatorial object has some required property. So in the object we care about today is like, whether some potential construction has this local correction algorithm. We'll take that property and encode it into a family of satisfiable XOR formulas. So basically, the fact that this combinatorial object has a local correction algorithm will encode it as these set of XOR formulas must be satisfiable. Okay. Then what do? Well, then I'm going to pick a random element of this family and try to refute it, try to prove that this random element is in fact not satisfiable. And then, I'm done. Okay. So, this description sounds actually quite nice, because you might imagine that the kind of XOR formulas we'll get from this scheme has some randomness. I picked one element out of this family randomly. You might even suspect that, oh, there is a lot of work on random constraint satisfaction and refuting them and whatnot. So maybe, they will come in handy. Maybe we'll just apply techniques from there and win. It turns out that you don't win so easily. The reason is that usually when we analyze random constraint satisfaction instances, the number of random bits that go into generation of the instance is way more than the number of variables. This makes sense. You're trying to, for example, rule out all possible 2 to the n assignments. For this, you will need like, tail bounds that look like 2 to the minus n. This will only happen if the number of random bits, is more than n. Otherwise, of course, you can't expect such tail bounds to be true in the first place. Yes? Makes sense? So in general, the random CSP business kind of fails you because, it requires way more randomness than the number of variables. In our setting, for example, in this cubic lower bound, we will end up with formulas with n variables and n to the 1/3 random bits. So, the number of random bits is way, way tinier than, the number of variables. in the result, in the title, the number of bits we'll have is just polylog n. So it's even tinier. So somehow, even though the formula is generated with very tiny amount of randomness, you somehow use the extra structure in the formulas to somehow show that, we can still get, proofs of refutation. And the way we will do it is, the idea is that, even though the probabilistic analysis of random CSPs requires n random bits because we are in some sense doing a union bound, if you have a simple enough algorithm that works, then, by virtue of simplicity of the algorithm, maybe you will succeed with very few random bits. Okay. This is spiel. You're not supposed to understand this, but at least that's the intuition. Okay. That, somehow you will prove this formula as unsatisfiable by analyzing an algorithm. It will be somewhat efficient. This was not the point of it. But, in some sense, that's the way you actually prove this formula is unsatisfiable. So even though, you could in principle prove it by any means, we'll design an algorithm to prove that this formula is unsatisfiable. Okay, good. Any question about this spiel? Yeah.
So, I mean, why did you think this worked? It's a great idea, but it's just, if I looked at this, I would have been like, oh, there's no way this would work, right? Like, how would you?
Good question. So it's a good question because that's exactly what I wanted to tell you next. But I won't again write down because this is spiel. So the way we began this work is we were looking at really constraint satisfaction. So you can see why I don't know that much about local codes is because, I'm not a local codes person. I actually, think a lot about random instances of, constraint satisfaction formulas and how to analyze their value, how to design algorithms for them. And one thing we were interested in, which is, with Peter and Venkat, was how to design algorithms that work for so-called semi-random constraint satisfaction instances. Semi-random means that in your SAT formula, the clause structure is completely arbitrary. So which triples appear in your constraints, you have no control over that. The literal patterns, the negation patterns, they're going to be random. So it's in some sense, reducing the amount of randomness that you typically have in random SAT instances. And the question was, can you somehow design algorithms that work for such random instances too? And we succeeded in doing that in 3 years ago. And the cool part was that, we were using very little randomness. So then, it was natural to wonder if we can go in directions where we reduce the randomness even further. Once you do it a little bit, you try to decrease it. And one natural point where, such situations occurred for us is LDCs. So the idea, by the way, of that these could be relevant for the LDCs came via a connection to a certain combinatorial problem. Again, I won't discuss that right now, but there is a hypergraph mode bound that we prove using, the same idea. And once we proved that, Omar Al-Rabia, the first person here, he had this brilliant insight that, the kind of combinatorial object we're analyzing seems very close to something that would yield LDC lower bounds. So eventually our proof did not quite look that way, but that's what got us started in this direction.
That's amazing.
Okay. Yeah. Okay, good. Yeah, I don't want to tell you too many stories. I want to tell you the math. Sorry about that. But good. So that's the spiel part. Let me now tell you how I'm going to do the rest of the proof. And write down the outline here. So, I'm going to tell you how to prove LDC lower bounds for 4 queries, not 3. So I'm not quite going to tell you the K cube result. I'm going to give you, what is the right result for 4 queries. This is because even numbers happen to be much simpler for illustration. So I'm going to tell you that. Then, this will allow me to, give you a hand-wavy heuristic for reasoning about when this technique will work. So, I'll say extract heuristic. And, well, then, the third part is to make the heuristic work for LCCs. I'll show you, how, I guess, I'll not write down here, but, I'll expand how I'm going to do LCCs once I get to it, okay? But that's our plan. I'm going to first tell you how to do that result a little bit, and then how this works, and hopefully this will be useful. You get 2 for the price of 1, right? You get at least to get about 1 more result. Good. So here is what I'm going to prove for you. in the next 15 to 20 minutes. I'm going to prove that for every 4 LDC, n must be larger than k squared. Okay, so you can see it's different from k cube, but that's because it's for 4 LDCs. This is what I want to prove to you next. Good, and I'm only going to work over f2 to the k, and you can imagine that the codes are linear. Okay. So the first thing I want to tell you is a combinatorial characterization of LDCs. Okay, this is what basically will help us build these XOR formulas that we're going to analyze. Okay. So let's look at the sets that you like, the queries that you will do to decode one of the bits. Okay, so remember LDCs means local decoding. So you're going to decode only the k of the message bits, which are the first k bits in the code word. Okay, so how might an algorithm for decoding this look like? Well, you're going to query some carefully chosen 4 tuples of bits in the corrected code word y, and do something to them. Yes. So it turns out with only like some little bit of patchwork, you can assume that the 4 bits you choose to decode any of the message bits are in fact non-adaptively chosen. Like in principle, you could do like one after another, select read one bit and then decide based on its value what to do for next. But it's not so hard. It's very, very, it's pretty straightforward to show that you can just assume that you choose 4 bits at once. Okay. So you can assume that the query sets for decoding any bit are non-adaptively chosen. Next, you might imagine that because I have to tolerate delta fraction corruptions, I'll have to somehow spread these query sets all around the code word. If I restrict too much to any single part, I'll be in trouble because then the adversary could focus their errors in that part. Okay. So it turns out you can basically assume, again with some cleanup, that the query sets, like the set of queries that all decode to, let's say, the first message bit are in fact disjoint. Okay, so that's meaning that I will never query. It's like in some sense I'll have in some sense some order n 4 tuples which are pairwise disjoint that will work to decode any given bit. Okay, so what that means is that for each of the k message bits, I actually have a hypergraph matching, meaning just like disjoint collection of 4 tuples. Okay. And each of the 4 tuple in the list for 1 can help you decode the first bit, and then similarly for second bit and so on. Okay. Next, because you want to tolerate constant fraction of the corruptions, it turns out it implies that these matchings are large. It should make sense, right? Like I should have a large collection of matchings because if they're only small, then matching edges, because otherwise if they're small, then I'll focus the errors only on the small part they touch. Okay. So what that means is that these matchings are omega n size. Okay, so they cover basically constant fraction of the bits of the code word. Okay. So local decoding means that for each of the 1 through k message bits, you have an omega n size matching. Okay, that tells you the query sets that you can use to decode that bit. Okay. Now, one last simplification. You can in fact fix your decoding algorithm. It turns out if the code is linear, like if the encoding map E is linear, then you can assume in fact that the decoding map is also linear. With some cleanup. What that means is that the decoding simply takes any, one of the 4 tuples in the list for H1 and, adds those bits modulo 2. That's it. Okay, so it's an extremely simple characterization of how algorithms work. The local decoding algorithms work. To decode the first bit, I pick one of the 4 tuples in this matching at random and add them what to, or XOR them. That's it. Does it make sense? I did not quite prove it to you, but I waved my hands frantically enough that you see it has to work, right? I hope this makes sense. Okay. Good. So, local decoding means that I have an omega n size matching for which, I can just take a 4 tuple and XOR them to decode any of the bits. I'm going to, in fact, assume that my matching is n over 4 size. This is, cheating. But, I promise I will not cheat. It's like, I will not overuse this assumption. Okay. I just don't want to remember another parameter here. Okay. Good. So I have, I have k perfect matchings, perfect hypergraph matchings of the decoding sets. Any question about like this characterization? Yeah.
Is it only for linear LDCs or also nonlinear?
Yeah, so that result works. This result works for nonlinear too, but I'm not going to explain how in this talk. Okay, so I'm going to make all the simplification that work for linear. You can ask me offline. It's not hard, but it's a little too distracting. Any other question? Yes.
Could you explain the non-adaptability? So why can you assume that it's non-adaptable?
Good. So, in some sense, you can basically guess the answers, and, it basically decreases the advantage by some 2 to the 4 factor. Like, if I had half this epsilon advantage, I'll just guess the answers and do according to them. And yeah, I lose some factor 16 and it doesn't matter. Does it make sense?
Yeah.
Any other questions? Good. Excellent. All right. So now, once I've described this combinatorial characterization to you, it is very, very easy to write down the XOR formulas that encode the constraints that local decoding with this hypergraph matching structure works. Okay. My formulas are simply going to say for every possible message, any query set correctly decodes the bit. That's my formula. Okay. So I'm going to write it down for you. So here are the formulas. So B is, think of are the message bits. Then for every I, for every 4 tuple C in ith matching, so the decoding sets, the XOR of the 4 bits in C correctly computes the ith bit, meaning B sub I. Okay. So say for all B, there exists an X, namely the code word corresponding to the message B, such that okay, so let me write it like this and I'll then come back to it. Does it make sense? Okay. And you can see it's a family of XOR formulas, 1 for every possible message. So they're really like 2 to the k different formulas I wrote. Yes?
Sorry, could you just parse through it again?
Sure, yes, yeah. My constraints are encoding that for any message, if I take the right code word, meaning like I take the encoding of that message, then on that message, local decoding must succeed with probability 1. Notice that it's an uncorrupted code word. For uncorrupted code, I didn't quite tell you this before, but for uncorrupted code words, the decoding must succeed with probability 1, meaning it should, every query set should give you the right answer. That's what this constraints encode. That for any B, if you take the corresponding code word, take any HI, take any 4 tuple in HI, XOR the relevant bits in C of the code word, then you must get the ith message bit back. This is just encoding that the local decoding succeeds on the code word. Make sense? Yeah.
So all this stuff like the constant fraction of error was like hidden in this reduction to the hypergraphs.
Yes. Yes. But that, is standard, so to speak. So yeah, there's no heavy lifting in that part. Like, that part has been understood for 20 years or so now. Any other questions? Good. Excellent. So we have XOR formulas before us, right? You can also see how to pick one randomly. Just choose B randomly. That gives you one XOR formula from this family at random. And we are going to somehow, prove that it's unsatisfiable if K is too large. Okay. Good. The whole strategy makes sense. All right, so now,
So formula, I mean the end of all the XORs over all the H's.
yes, yeah, sorry, yeah. So, once you fix a B, this is the whole formula, meaning this is the set of constraints I have. I merge all the constraints coming from all possible K matchings. Like, it's like, I get a formula once I fix B, and then I write down all the decoding constraints for every possible bit of B. And, that's my formula number 1. So for every B, there is a formula, and, I'm going to take B randomly and show that if K is too large, then this formula is unsatisfiable. Yes.
This question might be because I've seen some of your talks before, but just from my understanding can I think of the following abstraction? I have, I guess, n times k different equations or sets or something.
Yes.
Okay. And if I was able to find a subset of them where I guess you're not using in every matching, I'm not using something an even number of times, then I'm good.
Yes.
Or
that would be enough for linear code.
Or are you doing more? Are you gonna show that, or are you gonna show something harder, like something?
I'm actually going to prove to you that there are many such violated cycles, not just one.
Okay.
Like the proof would imply, like the proof I'm going to show you today, even though I'll not maybe transparently claim this today, it would imply that there is not just one, but many such cycles.
I think what I was asking is the like final object you're going to construct, which is like a subset of equations where you're not using something, where every matching is used, where at least one
matching is used an odd number of times. Yes. So let me, okay, given that given that, Yang mentioned this, let me, point this out. It's not so hard. So, how do you prove that a system of linear equations is unsatisfiable? Well, one way is to basically, do the following. Find some subset of equations, okay, such that their left-hand sides add up to 0. Okay, but the right-hand sides add up to, hopefully 1. Then you have a contradiction because 0 equals 1. Yes, this makes sense. It turns out it's the only way to prove linear equations unsatisfiable. Like if any system is unsatisfiable, there is always such a proof. It's not so hard either. Okay, so now if I add, so let's understand, if I'm going to take a bunch of equations and I'm going to add the right-hand sides. So the right-hand sides of my equations are correlated. For each BI. They're really like n over 4 different equations with the same right-hand side BI, right? If I use 2, equations with the same BI, well, they're going to cancel out. They're going to give me 0 no matter what BI I started with. So I'll never get 1. So if I have to get 0 equals 1, I must take a subset of equations such that there is at least one matching which contributes an odd number of edges. So that if the bit corresponds to the matching happen to be 1, then I get odd number of copies of it and I get 1. Okay. So this is in some sense, the refutation object that you need to prove that, there exists a collection of hyperedges, collection of equations like this that XOR out to 0 with the additional property that there is at least one of the matchings that contributes an odd number of hyperedges. So this is what Yang has pointed out. Okay, does it make sense? If it doesn't make sense, doesn't matter because we're not going to use this kind of reasoning today. Good. All right. So this is my set of equations that I'm going to prove unsatisfiable. Yes, please.
So I have a question. So what you're actually proving is that you're kind of mapping LDCs into the structure of disjoint matchings, and then what you're really proving is that these LDCs are not going to exist because you can't have an LDC, you can't have like an object that follows the structure and that decodes or decodes code words correctly.
Exactly.
So like kind of like the LDC property is in the structure or like the property that the LDC follows that structure.
Exactly. So let me repeat Pedro's point. It's a good one, right? So how is the LDC in some sense playing a role here? So LDC is saying that the constraints have like this union of disjoint, union of matching structure, right? That's giving you some structure in the kind of equations you have, right? And so what Pedro is saying is that somehow we are going to use this structure of the equations to show that very few bits of randomness are enough to prove unsatisfiability. Like that's the intuition. Good. All right. So to proceed with the proof, I'm going to make a notational switch on you. Oh, I guess I kind of already made it and you did not complain. So let me tell you why you should have complained. I should have taken B to be in 0, 1 to the K here, not plus minus 1. That's okay, you did not notice, no harm, no foul. But now I'm really going to think of B as plus minus 1. And, I'm going to go to the world where x's also take plus minus 1 values instead of 0, 1. And then addition becomes product. Okay. Good. So x sub c just means, the monomial with, monomial, which is like the product of x sub i's, x sub j's, where j is in c. Any questions about this?
Well, it's important.
It is. Yeah, it is important in some sense. You'll see. You'll see.
So one last point. I guess so far you haven't actually lost any equivalence. Like this is completely equivalent
Exactly.
to the original problem.
Yeah. Again, this is an amazing audience because all these are in somewhere there that I'm supposed to say it, but I'm glad somebody brings it up. So yeah, Young is absolutely right. This so far is a non-lossy reduction, right? There is a K comma N LDC if and only if, in some sense, there is some instantiation of the hypergraphs for which the system of equations is satisfiable, and vice versa, right? So we've lost nothing. Refuting one of these formulas is equivalent to showing the non-existence of an object. Okay. Good. All right. So what am I going to do now? I'm going to define the following polynomial. Everything has become plus minus 1, without you noticing. So x also lives in plus minus 1 to the n. I might have been writing x is plus minus 1 to the n even without telling you. Everything is okay. Nobody noticed. I'm going to write down the following polynomial. I from 1 through k, b sub I, okay. So, the short answer to your question, Yotam, was that, I'm going to do plus minus 1 because, in some sense, I'm going to treat all these polynomials as polynomials over the reals now. Okay, so and plus minus 1 is in some sense the right thing to do when you're going to reals. Okay, good. So look at this polynomial. Okay, then I claim that for every b, there exists an x such that fx, let's call it f sub b of x, is at least k times n over 4. Okay, this is really trivial. All I'm saying is that, for every b, there is a code word corresponding to it that passes all the local decoding checks. Passes all the local decoding checks means that x sub c will evaluate to b sub I. So I get square of b sub I. So I'm simply counting the total number of hyper edges in the union of HIs. Each HI has n over 4 hyper edges. So it's k times n over 4. Make sense? So, just summarizing what we've already done here, for every b, we know that this polynomial takes a large value. Basically, it takes in some sense a value which is as large as it possibly could be on, plus minus 1 to the n. Okay. So what are we going to do? We're going to prove that for random b, in fact, this polynomial cannot be large. Okay. And the way I'm going to do this is by this idea of spectral refutation. So what I'm going to do is write f sub b as quadratic form of a matrix. So let me write it like this on some vector. So I'm going to invent a matrix, okay, and show you that fb can be written as a quadratic form of this matrix. And then, bound the operator norm of this matrix in order to get an upper bound in the value of f. Okay. This idea of relating a polynomial to, quadratic form of a matrix and then using, the operator norm upper bound is called spectral refutation. And it has a long, long history in CSP refutation world, which is what we're going to do here. Okay. So how are we going to do this? I'm going to first define, x. I have not told you what v is. It's not going to be x. Okay. I notice that if it's x, then it's a quadratic polynomial, first of all. But in fact, v is going to be, okay, I'll come to it. Good. So I'm going to write fb, in fact, let's answer the question right away. I'm basically going to invent one matrix for each matching. So I'll have A1 through AK, okay? That's how A is going to look. I have not told you what this is yet, just telling you the form of it. And V is going to be the vector of degree L, homogeneous degree L monomials in X. Okay? L is a parameter. Okay, so I'm going to choose L later on. So for some parameter L, I'm going to take the vector X to the circle L. I'm writing circle because it's not quite a tensor product. I only have L-wise multilinear monomials populated. So the dimension of X to the circle L is N choose L. I'm telling you all these trivial facts so that you have time to digest the notation. Okay, any questions about this? Yeah?
For LDCs, L will be 2.
No. For 4 LDCs, L would be somewhat huge, in fact. You'll see eventually that L is going to be square root of small l. So this matrix is going to be huge. I have not told you what these dimensions are. Okay. So even though I have FB, which is a quartic polynomial, it's a degree 4 polynomial on the left, I'm actually going to write it formally as a degree 2L polynomial. Okay. Good. So, let me describe to you what AIs are without further ado. AI is going to be a matrix indexed by subsets of n of size exactly n. That's maybe not a surprise given what I'm taking a quadratic form on, right? And if I have S and T, now I have to tell you, what are the entries of this matrix. This matrix is going to be, in fact, an adjacency matrix. Entries are going to be 0 or 1. Okay, so it's really a graph. And this graph has an edge between two subsets S and T if and only if the symmetric difference of S and T as subsets of N is an element of HI. Okay, so let's, it's in the end very, very easy, but I want to tell you some trivial facts so that you have time to digest, what's going on. So remember, the elements of HI are 4 tuples. Okay, S and T are huge sets. I promised you that they're going to be like root n size eventually. Okay, so even though this graph is on n choose L, n to the L vertices, it is very, very sparse. S has an edge to T only if the symmetric difference of S and T happens to be a set of size 4. In fact, that set of size 4 lives in H sub I. Okay, how does it happen that two sets of size L happen to have a symmetric difference that lives in H sub I? Well, the only way it can happen is if S and T intersect in all but 2 elements. Okay, so they share L minus 2 elements, which when you add them or take symmetric difference cancel out. And the remaining 2 elements which they don't share combine together to give you the 4 tuple you want. That's the only way this happens. Does that make sense? So even though this is a huge graph, it is actually a very sparse graph. Okay, it's in particular, its degree, no matter what hypergraph you start with, cannot be more than L square, whatever. Because it's that's the number of pairs you can have incident. Any questions about this object so far? So this 1, 0 otherwise. Okay.
So how do you choose the L again?
I have not told you how that. Yeah, so the argument will tell me what L to choose. So L, think of it as a parameter. So I'm building a family of upper bounds on F sub B, and one of them is going to work.
It needs to be large enough so that you have some ones in the matrix.
Yeah, we'll get to that. Yeah, we'll get to that in 10 minutes. Okay, good. All right. So let's think about this. Okay, good. Erase things. Okay, good. So let's prove what I wrote over there. Actually, what I wrote over there is not exactly accurate. There's going to be a scaling that I'm missing. We'll see. Okay, so let's understand what happens to X, the quadratic form of X circle L, some BI, actually, let's do it for a single AI first. So I claim that this actually equals some X sub C times and the reason I can write it very fast is because it's trivial. Okay, so why is this claim going to be true? So if you expand this quadratic form out, what do you get? You get sum over all possible ST of size L. Then you get, the monomials XS, XT from the two sides. And then you get the STF entry of AI. Okay? But AI ST is non-zero only if S and T symmetric difference out to one of the C's in H sub I, in which case XS times XT is equal to X sub C, right? Now the same C actually contributes to many different pairs S sub T. So what you really get is sum over C in HI, sum over pairs ST such that S symmetric difference T is C of X sub C, right? So now, I'm clearly because of symmetry, I'm going to have the same number of copies of any C. The question is how many, okay? And that's exactly how many, that's how I counted it. So how do you count it? I have S and T, they must intersect in L minus 2 elements. That's the choice of, the L minus 2 elements, and this is outside the C you're looking at, right? And then, there is 4 choose 2 ways to split a pair into, a 4 tuple into, 2 pairs, okay? Good, yeah. So let's call this number delta, and then just write delta here. Okay, so far so good? Yeah, good. All right, so this is good. If I sum, okay, let me not be too stingy, I guess. Okay, so I guess you see that expression up to like this delta factor, you see why, FB is a quadratic form. Even though FB is a quadratic polynomial, and even though formally the right-hand side is a degree 2L polynomial, the equality holds, okay? So now what am I gonna do? I'm going to erase this and observe that for any B, FB of X is clearly at most the L2 square norm of the vector X to the circle L times the spectral norm or operator norm of the matrix I'm taking it on. Yeah, this also makes sense? Yes? Good. So what's the L2 square norm of X circle L, if it's all making sense?
Into the L.
N to Z, exactly, right? Like X is a plus minus 1 vector. So X to the circle L is monomials in plus minus 1. So it's like plus minus 1. When I take L2 norm, it doesn't matter what the signs are. It's going to be just, the number of non-zero entries. It's going to be N choose L. Yeah? So let's write it as capital N, the size of the matrix. That's just N choose L, notation for N choose L, times the spectral norm of this guy. So that, we have to basically compute the spectral norm of, this matrix, right? Good. So now, let me tell you about an inequality that, if it's like, super simple and it completes the proof, but, I want to tell you in 2 minutes what this inequality is, okay? So instead of matrices, if you just had scalars here, do you know how to upper bound this? If I had like, some I, Bi, let me back up and tell you one thing I forgot. B is random, okay? So now we are like trying to bound the norm, the spectral norm of a random matrix, okay? A random signed sum of matrices. And the question I'm asking is, suppose BIs are random, like uniform and random, but capital AIs happen to be scalars, okay? How would you bound this? How does this expression look? Exactly, this is what you would use. You will use the Khinchin inequality, okay? It's simply, if the Khinchin inequality says that, if you have a sum of scalars, small ai, and they're all bounded, let's say, at most 1 in magnitude, okay? Then, the signed sum of them basically has the square root cancellations you expect. It's going to look like square root of the number of terms. Okay, this makes sense?
Are you normalizing this expression by delta or something like this?
Sorry, Klim, could you repeat that?
Are you normalizing this expression by some delta or?
No. Sorry, this. Okay, my bad thing. This is. Does that help?
No, I'm asking if FB is less or equal the thing that you wrote. You need to normalize it somehow because.
Right. So you're saying I missed this, right?
Yeah.
Sorry. Yes, absolutely.
Okay.
Good. So yeah. So if capital AIs were scalars, you apply the Kinchen inequality, and if capital AIs are matrices, what should you apply? Should apply the matrix Kinchen inequality. That's not a big surprise. There is such an inequality. I'm just going to write down what it gives for you. But if you're interested, in the fall, I'll teach basically a whole class on just uses of Kinchen inequality. So, you're happy to learn it over the course of a semester instead of in 5 minutes. Okay, so this is going to be at most square root log capital N times some AI square. Okay, so again, the trick to understand what's going on is to think of what it would have been like if capital AIs were really scalars. If they were scalars, then the variance of this random variable would simply be the sum of squares of this coefficients AIs. That's what I have here. Okay, but they're not scalars. Okay, they're matrices. So I'm taking the standard deviation, but in the spectral norm. So I'm taking the spectral norm and taking the square root. Okay. Now, you don't lose anything else in the scalar Kinchen inequality, but for matrices, you pay in the dimension of the matrices. That's this cost, square root log of the number of rows in the matrix. I'm assuming, by the way, the matrices are symmetric here. So it's a square root log of the number of rows or columns in the matrix. Okay, does it make sense? I mean, I don't know if you've seen this before. If you haven't, take it on faith for now. Okay, good. Okay, great. So that's good. We've computed this expression. So now what? Now we're going to upper bound this. Actually, I'm going to use a very trivial upper bound. Okay. Remember that AI is a graph, right? AI is a adjacency matrix of a graph. Let's say, its degree is D max. Okay. The largest degree of any vertex in AI, let's say, is D max. Then the spectral norm of any single AI is at most D max. You agree? A degree D graph has spectral norm at most D. That's all I'm using, okay? So if AI has spectral norm D, then AI square has spectral norm at most square of D, or D max squared. Yes? And then by triangle inequality, this thing is no more than square root K times D max squared. Agree? Yes, that's all I'm going to use. Okay. All right. So now, let's reason about what's happening over here. Okay. I could have done the calculation for you, but I won't because I want to tell you a little bit about LCCs too. So one thing I want to observe for you is that if D max happens to be way too large compared to the average degree of AI, this bound is going to be vacuous. It's maybe not so surprising that, if the graph happens to be very irregular, then, the spectral norm comes from one of the large rows and it's going to be kind of a, weirdo overestimate, okay? If this is not 100% clear, which it probably isn't, take it on faith, okay? So in order for this upper bound to be non-vacuous, to be interesting, you actually need that AIs are, at least approximately speaking, regular, okay? That the degrees of the vertices in AIs are not that different from each other. Okay, so we're going to need, I'm still going to write here. So I want, let's say, within log small n factors, all the degrees to be equal. Okay. So, let's reason about whether this could be true. Okay. Actually, before we reason about it, let's see why it helps. Okay. Suppose I can replace D max by D average. Suppose, the graph happened to be, super regular, all the degrees were equal. Okay. If all the degrees were equal, then this, would be square root k times D average. Yes? If that's true, then let's see what happens. I have, delta times fb of x, which we know is, if x is a code word of b, we know, fb of x is at least k times n over 4 large, right? And then, I get this delta tagged in, yeah? So that's, a lower bound on this expression. On the other hand, we are saying it's also at most n times square root log n times square root k times the average. Okay, so this is the inequality we have before us. So now, let's look at, what this expression looks like. This is basically the total number of edges in AI, right? Remember how we got this? Like, this is the n over 4 edges in the matching, and each edge appears capital delta times. That's the scaling factor over there. Yes? So this is simply the total number of edges. And, I have over here n times d average, which is number of vertices times average degree, which is also equal to the total number of edges. Okay? So those parts cancel out. So what do I get? I get that k is at most square root k times square root of log capital N. Yes? So that resolves to k is at most log capital N. And remember, capital N is the number of vertices in this AIs. So that's n choose L, so which is about L log N. Okay? This makes sense? So if all went according to plan, you would end up with k, which is at most, you end up with an upper bound that k is at most about L, up to some log factors. Like log n factors are not going to be bothered for us. So, L is what is the substantial cost here. But you'll say, okay, this seems great. Let's just choose L to be as small as possible. Okay. What's going to break?
The average degree part.
Yeah, exactly. Okay. So now let's understand, whether we can actually make these graphs approximately regular. When can we make these graphs approximately regular? So, let's compute the average. Let's still do it over here. It's going to use the last four. Let's compute the average over here. So the average, okay, so let's see how many edges do I have? N over 4 is the number of hyper edges in AI. Each of them gives me n minus 4, L minus 2, and there are some constants I'm going to ignore. That's the total number of, up to constant factors, that's the total number of edges in AI. To take average, I divide by the number of vertices. And this expression, if you look at it, this expression is just L square over N square times N. So this looks like L square over N. Okay? Still makes sense? So now notice that if L is much tinier than square root of N, then the average degree is much tinier than 1. Okay? But the max degree is always at least 1. There's going to be some edge. Okay? So if you choose L to be much, much tinier compared to square root of N, then you can never hope to get approximate regularity because average degree is, very, very tiny, while max degree is always at least 1. So in order for approximate regularity to even make sense, you've got to ensure that this is bigger than 1, which implies that L must be at least square root of N. Does that make sense? So now, our whole game is to ensure that this is somehow enough. That somehow we can take the matrix corresponding to L equals square root of N and make it regular. Ensure that it's regular, okay? This is just a sanity check, and you're saying that we want to go as close as possible to this sanity check as possible. Okay. So let me, so I won't, tell you the details here. I'm just gonna tell you that the matrices that we have are not actually regular. And the reason is very, very simple. You can look at, I have these n/4 matchings in, let's say, H1. You can look at the sets S that use two vertices from, let's say, the first L/2 hyperedges. That's going to be a set of size L. And it has basically degree L/2. It is incident on L/2 hyperedges. That makes sense? We want, average degree to look very, very close to L square over n. We are choosing L to be about root n. So L square over n, you should think of it as like a constant. Okay. We want average degree to be a constant, but I'm saying that there's clearly a vertex with degree which is comparable to L. And the vertex basically arises by carefully looking at these matchings and looking at like the first L/2 matchings, taking two vertex each from each of the hyperedges. Okay, then, I can basically, then I'm incident. I have edges incident on me according to every one of the L/2 hyperedges, so my degree is L/2. Okay. So this is bad. We don't have approximate regularity, but we still win because we can basically show that the fraction of vertices for which this happens is extremely small. Okay, so then, what you have to do is like somehow throw away these vertices and show that it doesn't really cost anything to this argument. It's actually very simple, but I'm not going to do it here. Okay. And then, you basically do get approximate regularity after throwing away some outlier vertices, and then the whole argument works out. Okay, so I'm going to be this level of sketchy for this part of the proof. Yes.
Like here, you didn't really need a random B, you just need the existence of a B. That gives you.
Excellent. Yes. So for this proof to work, I only need to have that there is a B for which I can make the spectral norm small. The proof is using a random B.
But would this not reduce to some kind of like discrepancy problem?
It is a discrepancy problem, and I have tried to attack it from that end with no success. So one use of this talk is that there are lots of people in the audience, who have analyzed random matrices. If you can help us, that would be great. Yes.
If this somehow also extends to nonlinear codes, then doesn't this mean, like, it's not that you can take a locally decodable code or a non-locally decodable code, remove one element from the message space, and then like hope that this will become locally decodable. I mean, to prove a lower bound, this must fail for a random B, right? Not just for existence of one specific one. At least
so I think you're both right and wrong. Let me explain why you might be wrong formally speaking, because you want, at least formally speaking, that the decoding should work for every B.
Yeah.
Right. So in principle, if you find me a B for which the decoding equations fails, you've proven your job. You've done the job of like showing that the code doesn't exist.
Yeah.
But you're also right because you're indeed right. You can somehow take this code which is good on average and make it into a code which is good everywhere. So it kind of has to be that many B's fail. It can't possibly be that there's only one B that fails. Yeah, good points. Good. Okay, so that's the LDC part. Here's what I'm going to remember as a message from you. Okay. One is that we needed to ensure that the AIs have D average, which is much bigger than 1. Otherwise, the proof did not work. Okay. I'm going to call this the density condition. The other part I'm going to remember is that I wanted, D max to be related to D average, like not too much larger than D average. So I'm going to call it approximate regularity. Okay. So if you can somehow build a matrix, okay, which happens to be a Rademacher signed sum, like a signed sum of some matrices, the constituent matrices have the property that they have density at least 1, meaning like the average degree is large, and it is approximately regular, then you could hope to repeat this argument. Okay. Now, for LDCs, I know of no better argument. Okay. This is, even though in some sense it looks very non-tight, it is as good as we have at the moment. Now, what I want to argue to you that for LCCs, you can do a bit better. Okay. So, let's go back to this board. Erase some stuff.
So,
Yeah.
So just one, could you remind me the how Young's intuition is here? Like you want to find a set of constraints such that zero is
Yeah.
that part.
Right, yeah. So in some sense, you can prove that the spectral norm could not have been small if that object did not exist. Okay, this is a tautology because if what I promised earlier is true, it has to be true. What I'm saying is that, if the object Young discussed does not exist, like this one matching odd subset of things that add up to zero, then you can prove that the spectral norm cannot be small. Now, this is in some sense just implied by what I made earlier, but you can make this concrete by, relating the spectral norm of this matrix to its moments. So you can take trace of like some high power of this matrix. And then you can show that when you expand the box, the kind of terms that contribute are precisely the kind of terms Young was pointing out. That's basically how you relate the two things, directly. Does that make sense?
So do you mean like are they actually the same thing?
Yeah, they are actually the same thing. But just like I answered Young, this argument ends up proving that there is not just one, but there are many, such linear dependencies which use odd number of things from some HI. Yeah, good, excellent. All right, so now let's. I have it here already. So let's go to LCCs, and just like I told you, this combinatorial characterization of LDCs. There's actually a very analogous characterization of LCCs, which just says that the matchings exist not just for the first k bits or the k bits of messages, but in fact for all the code word bits. So it's very easy to draw. It's very easy to draw what this object looks like. That's it. That's the combinatorial characterization of LCCs, okay? And now, I can do the same trick I did on you earlier. I can write down, that the equations for local corrections succeed. This is going to be a formula, okay? So I'm going to write down that for every B, every message, there exists an X such that for every I, for every C in the correction set for H, for ith bit of the code word, X sub C equals X sub I. Notice that I'm not writing B sub I because I'm not just decoding the message bits now. I'm correcting all possible code word bits. So all the equations say is that if I take a tuple from the ith matching, take the addition of them mod 2, then I correctly recover the ith bit of the code word. Does that make sense? Yeah? So really, in some sense, B doesn't play directly a role at all here. All we are saying is that, every code word satisfies the system of equations. Okay? You have a question, Yotam?
You also want to say that like the first k bits of X are, like you want them to be distinct, right? Otherwise, this is like.
What do you mean? These equations simply say that, the local correction succeeds for all the bits of the code word. Now, what you're observing is that in particular, it succeeds for the first k bits. And the first k bits, remember I promised you that they are the message bits. For the first k bits, for I in 1 through k, I can in fact write down.
You're saying you have to write this, right? Otherwise, you can just take X to be 1, all 1.
I have not told you that it's an unsatisfiable system yet, but yes, I think you are. Yeah, I think you're right.
To capture the LCC, right? Otherwise, it would not be. If you didn't try that the first k bits are BI, you can say for every B, take X to be 1.
Okay, the way I was thinking was like I was bound in the dimension of solution space if I don't write down the B's. I think I'm going to do the proof in your way. So let me do this. Yeah. But okay, it's okay. Maybe the discussion that was a little bit confusing, but this is it, right? Like I'm saying the first k bits, are the messages. So for them, my local decoding checks succeed. And for the remaining bits, the local correction sets succeed. Sound good? Okay, good. So now, you could say, okay, there are many more equations. They're kind of weird. Some of them have right-hand sides B. Some of them have, in some sense, no real right-hand side, so to speak. But, there are equations nonetheless, and can you use like this many more equations to your advantage? Can you show that this system might in fact be much less satisfiable in some sense. Like it should become unsatisfiable at a much smaller k because you have like a denser system. That's the intuition. That's the question you're asking. Somehow, the previous techniques were not able to win by this, even though like in some sense, this is mostly a restatement of what people knew all along. What we did not have a way to use like this extra matchings. Okay. So what I'm now going to tell you is, how I'm actually going to build K matrices. So exactly an expression of this sort. Okay. But this time, my matrices will depend not just on the first K matchings, but they will actually use information from the remaining n minus K2. Okay. This is in some sense the key idea 0. Okay. Good. So it's kind of nice to, okay.
Sorry, just because it's easier for me to think about, what is a combinatorial interpretation of this? If there is one, that's nice.
I think it's exactly the same, but you want like the odd thing to come from the first K matchings.
Got it. Okay. And the rest you don't care about.
Yeah. Good. So you want linear dependency, you can use any hyperedges from the rest of the matchings to help build your linear dependency, but you should use odd number of things from one of the first K HIs. Again, like ignore this comment, if you didn't quite follow this. Okay. Good. So let me tell you how we build this. So what I'm going to actually tell you is a construction that works to give a lower bound, let me say, n at least k to the 4 for 3 LCCs. Okay. So this is not the best. I promised you exponential. I'm actually not even going to tell you this, but the construction I'm going to show you would already yield k to the 4. Okay. And it's like significantly simpler than the general scheme to analyze. So it's in some sense the right place to start if you're like somehow looking at the paper. Okay. So here is how I'm going to do this. So the idea is you have a system of XOR equations. If you gave them to a proof complexity theorist and ask them like, find me like a proof that they are unsatisfiable, what would they do? They would do some resolution. They would do some derivations. They like take these equations and say they imply these further new equations and they apply this more new equations. And at some point they imply that, 1 equals 0 or something. This is how proof complexity theorists would think. Okay. That's what we are going to do. We're going to derive new equations by combining equations from the first K matchings with some equations from the remaining n minus K. Okay. So I'm going to call these equations by how they look combinatorially. I'm going to call them two chains. Okay. Here is how they look. I'm going to take one equation, basically a triple, from one of the first K matchings. Let's say it is from the ith matching. I'm going to write I here. Then I'm going to take one more equation now, and it's going to be somewhat carefully chosen. I'm going to read, let's say, these are bits 3, 4, 5. Okay. I'm going to take any one of these 3 bits. Okay. So I'm going to, let's say, choose 3 or 4 or 5 and go to matching number 3 or 4 or 5 and pick an arbitrary constraint. That makes sense? So I choose, I start from one of the labels in 1 through K. So I is in K. I pick any hyperedge in H sub I. It tells me 3 possible bits. I go to their correction sets and pick a tuple from that correction set. So I get something like this. These don't intersect, but remember, one of the bits of the first hyperedge told me the matching to pick the second hyperedge from. Okay, does that make sense? So some notation, I'm going to call this head. I'm going to call this pivot. And, just like in the second step, I'll have some W1 over here, some designated 1 vertex out of 3. I'm going to call that for now the tail. Okay, so it's a chain. It has a head, it has a pivot and a tail. Okay. Yeah.
Could you explain that again, please?
Yeah. So, I'm going to take one one of the first K matchings. These are the ones that appear with like a BI. The corresponding equations appear with a BI on the right hand side. So let's say I go to H sub I, then I pick an arbitrary triple in the correction set for H sub I. Okay, that's this triple number 1. Let's call it C0. C0 has 3 things. It's a triple. Pick any one of the 3 things. Let's say W0. And then go to matching HW0, meaning the set that corrects the W0th bit. And choose an arbitrary triple from that matching. So this is C1. And this is just notational purposes. I'm going to designate one of the 3 bits in C1 as W1. Yeah, makes sense? It is just like one particular way to combine 2 equations. I'm going to take like, the 2 equations corresponding to the two of these hyperedges and write down what the combined equation looks like. Okay?
You always have to start with one of the first K bits.
Yes. That's how I'm going to get like an equation with always like some right-hand side that depends on one of the BIs. Okay? So what does it look like? So, I know here that BI equals XC0. That's the decoding equation for the first hyperedge. I also know that XW0 equals XC1 because I picked C1 from HW0, right? Remember, these are all plus minus 1, so I can just make this 1 and multiply XW0 on the other side. And now what do? I just multiply the 2 equations. Okay? And now, remember C0 has W0 inside of it, this variable. I have a W0 over here. So that variable squares out, cancels out, okay? So I get, I have a new equation which somehow combines 2 equations, one from the first K matchings and one from the remaining n minus K. Okay? This is it. This is my operation. I'm going to now look at these equations and do the whole damn thing again. Build those matrices and all. And then, the magic would be that I'll show you that the density has increased. The average has increased. And further, with, somewhat more work, I can still argue approximate regularity. So everything goes through. Okay. So let me now, I still have 10 minutes there, right?
As much as
Okay.
10 minutes that they need.
Okay. So now, I'll tell you, why these equations are better. Okay. Yeah.
So why just 2?
Oh, yeah, exactly. So the final proof works by taking long chains. The final proof works by taking log and length chains. But it's, it's a lot hairier. So, I'll just restrict to 2 for the purpose of the talk.
So you take all possible chains.
I take all possible chains. Yeah. Okay, any questions about like the construction? Okay, good. So let's, think about this. So let's first think about, so I started with, equations which were 3 linear. They were triples, 3 sparse. I have gotten like larger sparsity now. Like, the degree of the monomials is larger. What is the degree? Let's examine it. This variable gets cancelled out with this W0, right? So I have 2 from here, 3 from here that remain uncancelled. So it is an arity 5 equation. So I started with like 3 XOR system and I built a 5 XOR system for myself. Okay, good. So now, I did 4 LDCs in the first part of the talk because even numbers are better. But it turns out that, I have arrived with an odd number and there is no way to get rid of it. If I have to talk about chains, I always end up with odd size arity. So I have to deal with it. So I'm going to tell you how we deal with it. Okay. We deal with it by making it even. Okay. So what I'm going to do now is take 2 chains. So take two chains, join them together so that, the arity becomes even. Okay. Good. So how am I going to do that? I'm going to draw it here. okay, so I had a chain coming from the left. So it was like, let's say I, C0, W0, C1, W1, this like the description I will remember for the left chain. I have a similar chain coming from the right. It starts at matching HJ. J is still in the first K matchings. Okay. Then, I do the same thing, but from the right. Okay. I pick a hyper edge. Then I, use one of the three things to tell me which matching to go to. Pick a hyper. But this time, when I pick C1 prime, I pick a C1 prime only if it contains the same W1. The tails of the two chains must match. Okay. That makes sense? So I'm going to join the two chains at the tail. So I only take like matching two chains and join them. That makes sense? Good. All right. So what happens? This thingy gave me like a 5 XOR equation. This thingy in general gives me another 5 variables, but one of them cancels out. In fact, like, two of them are equal. So one of them squares out. So I now get an 8 XOR equation. Like 5 plus 5 minus 2. Okay. These are even, and these are the ones I'm actually going to burn.
The right-hand side would be BI, BJ.
Yeah, so I'll come to, what we'll do. I'll come to that. Yeah. So basically, we are only going to, for any fixed I, we are going to choose exactly one J, and that's the only chains that will merge. Yes.
So why is it like a 5 XOR? Things may cancel more than that, right? When you merge two chains. And like when you have more chains, things may also.
Excellent question, right? So you're saying, why am I canceling only one variables? Maybe like, there are chains that intersect in pairs, and then I should really be canceling out the pairs. This in some sense is a problem, like, and knowing beforehand which one you should do is a problem. So in the end, the final proof really shows that, either one cancellation works or two cancellation works. So it's a very good point. It's unclear if I'll get to, that level of detail in this talk, but you have to worry about exactly what you said. The current construction would work if I assume a certain pseudo-random property of matchings, and then, you have to do something else to show why things are fine when that property doesn't hold. So I'll come to this bit, why it's okay to just cancel one variables, if the matchings are pseudo-random. Okay, good. Any other questions so far?
This is like the 1/8 that you.
No, that's not the 1/8. No, this is not the 1/8. Especially because this is just the proof for n to the 1 quarter.
No.
The 1/8 comes from something else because we are going to do log n chains. Like the chains are going to become very long to get the exponential lower bound. The 1/8 comes from like various log n losses. Most of them feel like extraneous.
Yeah. So it's not something that depends on the area.
It doesn't depend on the arity. Yeah. Good. Okay. Excellent. So let's now describe the matrices AI. Yes.
Sorry, a very quick question.
Yeah.
It seems like you could apply this technique also to the LDCs. There's something that obviously breaks down that.
Yeah, excellent question. So the story of the paper is that I did not know about the LCC problem. I only knew about the LDC problem. So in fact, for a while, we were trying to apply this technique to just LDCs. It turns out that, it doesn't work. It doesn't give you any improvements, even if you build chains and try to get, basically you don't get gain in the density as you might expect. And in some sense, the key observation really is that in LCCs, I think this technique gains you in density while in LDC it does not.
But you can't really apply it because the triple that you use, the C0, the three things might not be in the first.
There is a different way to build chains that makes sense in the LDC setting, but the issue is the same, that it doesn't really help. Good. Okay. So let me describe the matrices now. Okay. Like I'm going to be somewhat hand wavy, but I can write down the polynomial corresponding to these equations just like we did for 4 LDCs. Okay. The monomials will be the things that are uncancelled in pairs of two chains that intersect at the tail. Okay. So I have a polynomial, just like, I had FI's, just like, FB, I had like F sub B over there. I have a polynomial F sub B here, okay? And I'm going to write now a matrix that basically expresses that polynomial as a quadratic form, okay? So I have an arity 8 equation, right? A degree 8 polynomial. I'm going to write that degree 8 polynomial as a quadratic form of some matrix, okay? So my matrix A sub ij, so notice that, I have two bits, I and j, that are tagged on to the equation now, okay? So for each ij, I'm going to define the following matrix. It's gonna be indexed somewhat annoyingly, but it turns out like really important to make this choice, by a 4-tuple of sets. Each of these sets are in n choose n. So the number of vertices in this graph that I'm going to build, or like the matrix I'm building, is n choose L to the 4. Okay. So now I have to describe to you what does an edge mean, right? Like what does it mean that S0, S1, S0 prime, S1 prime is connected to the column index. Okay. So you can see where the 4 comes from. I have 4 hyperedges in merger of 2 chains. So what basically I'm going to ask this matrix to do is that the symmetric difference of S0 and T0 should be equal to the uncancelled vertices in C0. So notice that this vertex is cancelled out. So there are 2 vertices left. Yes? So S0 plus T0 should equal C0 minus W0. Similarly, S0 prime plus T0 prime should equal C0 prime minus W0 prime. S1 plus T1 equals C1 minus W1.
How do you know what is a W0, W0 prime, W1?
Was that a question?
How do you know W0, W1, or you're doing it for all?
I'm doing it for all.
Okay.
So I'm describing to you what does an edge look like corresponding to one of the mergers of pairs of 2 chains. Okay. So I want basically, the point is that in this collection of 4 hyperedges, each hyperedge has 2 uncancelled variables. The third one is always cancelled out in the way I built them. And I want the symmetric difference of the corresponding pair of sets to be exactly those uncancelled vertices. Okay, that's basically what these equations mean. Make sense? Okay, so now for my final act, I'm going to compute, the average degree of the graph. Okay, and this is the first heuristic that should tell you that we are on our way to win. Okay, so let's count the number of 2 chains first. How many 2 chains exist with head I? So if I fix the head, how many two chains do I have? Well, once I fix I assume perfect matchings. There are 3 matchings now, not 4. So I have n over 3 hyperedges to choose from. So I have n over 3 choices for C0, 3 choices for W0 within it. Once I've chosen W0, I'm in matching 8 sub W0. I have n over 3 choices of hyperedge C1 and 3 choices of W1 from within it. So the number of 2 chains beginning with I is exactly n squared. Okay? Good. What is the number of 2 chains, number of pairs of 2 chains that have heads I and j? So now they have to there are two chains that must intersect in their tails. Okay, there are n squared 2 chains on the left, n squared 2 chains on the right, and you can in fact show that the tails are basically all uniform. So all the W0s appear equally often. This is where I'm using perfectness of the matching. Okay, so exactly 1 over n fraction would basically have the same tails. So this gives you n squared times 1 over n equals n cubed. Does this make sense? Somewhat hand wavy, but does it make sense? Yeah. So there are exactly n cubed pairs of two chains that I can merge to form like this monomials I care about. Okay. So for a fixed I and j, I have n to the 4 different monomial constraints. Great. So now, let's estimate, how many edges I have in a sub ij, and what its average degree is. Okay. So how many edges do I have? So each of the n cubed pairs of two chains give me multiple edges. Let's count how many. Okay. So how many S0, S1, S0 prime, S1 prime, and T0, T1, T0 prime, T1 prime are there, such that, their whatever, coordinate-wise addition is equal to these equations. Like how many pairs of coordinates, pairs of vertices exist so that all these 4 equations are satisfied. Okay. So let's, look at the first equation. Okay. When is the first equation satisfied? When S0 and T0 XOR out, or like symmetric difference out, to the 2 vertices in the first hyperedge. Yes? This can happen if and only if S0 and T0 share all but one vertex. So that, the L-1 things completely cancel out, and the remaining 2 things basically give you the relevant pair. Okay? So you can see that I'm going to get some n minus some constant. Let me ignore that, and choose L-1 to the 4. Like, I'll pick the pairs S0, T0 that XOR out to the 2 things here. That's exactly n-1 choose n choose L-1. Then there's an n choose L-1 that I have for each of the 4 things. So I have n choose L-1 to the 4. Does that make sense? There's really n minus some constant, but I'm ignoring that. So that is the total number of edges you have. Okay. So let's, compute the average. So the number of vertices I have is n choose L to the 4. That is the number of edges I have. So, the average degree is going to be n cubed times L over n to the 4, which equals L to the 4 over n. Okay. And yeah, that's my final act, because as you notice, if L exceeds n to the 1/4 this time, then, the average degree becomes more than 1. So the point is that, at a smaller level L, I'm able to get density 1 or larger than 1. Okay. Now, if you repeat the same calculation, assuming that these AI matrices are approximately regular, then you get the whole equation works out exactly as I wrote earlier. And you get a bound which is that K is at most L. Okay. Just like, we did earlier. But this time, we only have to choose L larger than n to the 1/4 if you can somehow ensure approximate regularity. Okay, so this is like a lot more work here, but we can do it. Okay, even for 2 chains, unfortunately, it turns out to need lots of ideas. I had like half an hour more of material to tell you about that, but I'll not do that, and you can ask me offline instead. But anyway, like the punchline is that these matrices work in the sense that if you make the assumption that in the matchings I have over here, no pair appears too many times. No pair of variables is queried, let's say, more than once to begin with. Then you can show that, in fact, this calculation works out in the sense that, the AI matrices are approximately regular. Okay. And then, the problem that occurs is what Kunal was pointing out earlier. You can have like HIs that somehow query, like multiple HIs, manage to query the same pair of bits. So pair is somehow, much more important, some pair of codeword bits. In that setting, you need to do something else. Okay. But the intuition is that if HIs were random, like if I generated these matchings at random, then pairs will not really repeat. Most pairs will be queried, in fact, exactly once. Okay. So, for that pseudo-random setting where no pairs are queried too many times, the argument I said, in fact, can be made to work pretty easily. And then, yeah, you need to do quite a bit of more work to understand what happens to the case when there are heavy pairs. Yeah, that's all I guess I would, yeah.
Just about this, do you have a general reduction from codes where pairs might repeat to codes that pairs don't repeat?
No, we don't have a reduction, no. basically what we show is that you can build a different formula. So, we break the proof down into two cases. So we first show that in fact, if pairs don't repeat too often and the threshold is non-trivial, then in fact, this argument can be made to work. And that's, where some polynomial concentration plays a role. It turns out that because we have like a non-trivial leeway in how many pairs we can allow to repeat, in the case when, there are even more usages of the same pair, you get a lot of constraints by canceling out two variables instead of one. And so then, so in some sense, you still have fewer equations than here, but the additive of the equations is even smaller. So they're like, instead of 8 XOR, they become 6 XOR equations. And it turns out that the trade-off breaks in our favor then. Like you have smaller number of equations, but also like the degree is smaller. So you still win with the same idea. So you don't actually get a reduction to a code without the pairs. You just show that, even then the equations can be refuted. Yeah, sorry for going a lot over.
So thanks.
Thank you very much. It was really good talk.
More questions? Questions over lunch?